Hello, my name is Eden Kim, and today we're going to talk to you about NVMe over Fabric performance and the impact of host factors on iWARP, ROCEv2, and TCP, and comparing the performance to an Optane SSD LUN and an NVMe SSD LUN. So, look at NVMe over Fabric. The key point is that NVMe over Fabric allows disaggregation of cloud and data center compute and storage. This helps optimize access to SSD storage and servers at scale. NVMe over Fabric extends high-performance, low-latency NVMe protocol over networks. It enables memory-to-memory data flow, or RDMA, and allows bypass of local CPU resources and scale out to data processor unit servers. Disaggregation allows decoupling of workloads, servers, storage, and test. The IOProfiler allows the capture of real-world workloads on any logical server, and the CTS IO Generator can apply test IOs from any direct, remote, or Fabric server. So, NVMe over Fabric, what is it? Here, we can see an illustration of NVMe over Fabric. NVMe is a storage protocol optimized for flash storage. If you look on the left, you can see that PCIe is the low latency transport used for SSDs. NVMe over Fabric maps that protocol onto Fabric transports. On the right, in the gray box, you can see Fiber Channel, InfiniBand, and Ethernet. Today's presentation will compare Ethernet transports for RDMA iWARP, RDMA ROCEv2, and NVMe TCP. So, when we talk about NVMe optimization, we're looking at storage and server pools, real-world workloads, and Fabric storage. The server pools consist of enterprise, data center, VM, Fabric, and data processor units, with storage pools illustrated on the left, such as SSD clusters, just a bunch of flash, and Ethernet bunch of flash. CPU onload, offload is present with RDMA or TCP transport, and the workloads can be synthetic or real world from cloud and data center application IO captures. The storage tests we use can be done to direct, remote, virtual, and Fabric storage. The CTS IOProfiler is a real-world workload module that captures real-world workloads on any logical server or storage at the file system or block IO layer. In the illustration, you can see the IOProfiler capturing workloads from the cloud or the server or storage and going to a control server database from which real-world workloads are constructed. Once constructed, we can take a CTS IO Stimulus Generator and place it on any host or Fabric server to transmit test IOs to storage. So if we look at the red IO Stimulus Generators, they can be placed on the host server or target server, or they can be transmitted across Fabric storage from a host initiator across the Fabric to a target server. So NVMe over Fabric Ethernet transports, what are the differences? Here we're zooming in to see the three Ethernet transports that we'll discuss today. For RDMA ROCEv2, this is a low latency transport best suited for rack scale. However, it requires ROCE-capable network accelerator cards and switches. It is a TCP offload, and it bypasses local CPUs, but it's a lossy network, which may need priority flow control and other resources to make it lossless. We will be discussing CPU, offload, and lossy or lossless networks in the subsequent slides. RDMA iWARP is also low latency and scales well with large data centers. iWARP requires iWARP-capable NACs and switches, It also has TCP offload, but in this case is a lossless network. And then finally, NVMe over TCP is low latency and scales well on large data centers because it's easily supported on simple NIC switches. It has TCP onload, which means it uses local CPU resources to manage network activity, and it is a lossless network, i.e. there's no dropped packets. So host factors can impact performance. Examples of host factors include CPU and NVMe storage, the NIC, the maximum transmission unit frame size and frame rate, switch settings, and network topography. In today's presentation, we're going to focus on NVMe over fabric transports for RDMA offload and TCP onload. We're going to look at NVMe SSD attributes, workload content, and test settings. The following illustration shows the back-to-back test setup where we will have a host initiator applying test IOs across the NVMe fabric to target storage. We will select one of the three NVMe over fabric transports, and we'll be using either standard frame or jumbo frame MTU. The workloads will consist of both synthetic and real-world workloads. In future studies, we will add switches and storage heads and other network topology to the configuration to test the more full-scale NVMe over fabric. So let's talk about lossy versus lossless Ethernet networks. What does this mean? A lossy or best efforts network does not guarantee packet delivery or quality of service. ROCEv2 and TCP are examples of a lossy network. Lossless networks guarantee packet delivery. TCP over IP and iWARP are examples of lossless networks. Lossy networks often include priority flow control at L2 and differentiated service code point, or DSCP, at L3 to become lossless networks. And we'll look at this in the next slide. Offload versus onload, TCP and RDMA transports. So here we're taking a look at a NIC card on the left, which has TCP onload, and a network accelerator card, or a NAC card, on the right-hand side, which has offload. Onload and offload is looking at from the perspective of the host CPU. For TCP CPU onload, the TCP IP relies on protocol stack and consumes CPU cycles. The NIC uses the host CPU for TCP IP onload. CPUs can be fully saturated servicing high-speed 100 gigabit Ethernet, thereby adding latency to storage and compute IOs. TCP offload engines and network accelerator cards are not yet readily available for TCP. For RDMA or CPU offload, RDMA stands for Remote Direct Memory Access, and the network accelerator cards offload host CPU cycles. This gives you a high-performance, low-latency host offload, host bypass technology, thereby allowing direct memory-to-memory data communication over networks. But this requires an offload engine on a network accelerator card. This also reduces server resources dedicated to network functions from protocol stack servicing. There are two RDMA implementations, ROCE, which is lossy, and iWARP, which is lossless. MTU, standard versus jumbo frames. MTU stands for maximum transmission unit, which is the maximum IP packet size allowed without fragmentation. The standard frame size is 1500 byte versus a jumbo frame size, which is now 9000 byte. As you can see, there is more overhead for the 1500 byte versus 9000 byte because in both cases, you have other frames such as destination, source, MAC addresses, and frame type, followed by correction code packets. So on the left-hand side, you can see the percentage proportion of data to other frames and packets is much smaller than for the jumbo frame. The target LUN storage we're going to use are two types. We have an Optane 2.25 gigabyte LUN, which is comprised of 6 375 gigabyte Intel P4800 SSDs. And we have an NVMe 24 terabyte LUN, which is comprised of 6 4 terabyte Intel P4500s. The individual SSD specs target different ranges of performance. So we can see here the Optane spec is in the middle column for the 375 gigabyte, and the NVMe specs are on the right-hand side for the 4 terabyte. Optane has higher performance with symmetric read writes. So you can see the random 4K read writes are both at 550,000 IOPS at a queued up to 16. NVMe is asymmetric read write, where it has high reads, 4K reads of 656,500 versus random 4K writes of 111,500, both at queue depth of 256. You should also note that the NVMe has a higher bandwidth for sequential 128K read writes of 3,000 and 2,900 megabytes per second compared to 2,500 and 2,300 megabytes per second. However, while noting there's a difference in the SSD performance spec, the performance of the storage LUNs can be much different. Here we show the performance of random 4K read write and sequential 128K read write taken on the Optane 2.25 gigabyte LUN and the NVMe 24 terabyte LUN using iWARP at the standard frame size of 1500 byte. One thing you'll notice is that the performance is higher than what's stated for the individual SSDs. This is often due to factors that are in the stack, including the fact that IOs are pooled in RAM and can be faster than the underlying SSD. The NVMe LUN performance level is influenced by intervening layers of abstraction, which can mask and change SSD device performance. Issues such as IO pooling in RAM can be affected by read-throughs and write-throughs to media. There are quality of service policies, head node server considerations, and RAID strategies that also affect performance. And finally, response times can be affected by every layer in the stack between NVMe fabric space and storage. So our test plan objectives: we want to compare NVMe fabric transport. We want to compare MTU frame size. We want to compare storage LUNs, and we want to compare workloads. Here is a look at the test plan topology. There's 4 sections to look at. First, on the control server side, we have captured the real-world workloads and deposit them into the CTS database from which we can construct real-world workload test scripts. These synthetic and real-world test scripts are then sent to the CTS IO Stimulus Generator, which is mounted to the host server. The host server sees logical NVMe-oF fabric storage across the NVMe fabric to the target server. In the middle panel, you can see the NIC wire NIC, where we have an Intel E810 NIC on either side, connected by a 100 gigabit Ethernet wire. And we will be sending either standard 1500 byte or jumbo 9000 byte frames across ROCEv2, iWARP, or TCP. The 2 storage LUNs on the right are for Optane, higher performance 6 SSD LUN, and the NVMe lower performance, higher capacity SSD LUN. Looking at the test plan or test flow in a more simplistic view, well, we can see that we're starting with 2 types of workloads, synthetic and real world. The synthetic are corner case random 4K read write and sequential 128K read write, and real world workloads. One is a GPS nav portal, which is 100% write. One is a retail web portal, which is 65% read. And the last is a VDI storage cluster, which has a 75% write content. We change the MTU between standard 1500 byte and 9000 byte jumbo. We select one of each of the 3 transports, ROCEv2, iWARP, and TCP, and we apply them either to the Optane or the NVMe storage line. So let's take a look at real-world workloads and compare their content. On the left-hand side, you have a retail web portal real-world workload, and that's an IO stream map which shows you the IO streams that occur over a 24-hour period. The x-axis is time from midnight to the morning to midnight, and the y-axis shows you IOs and IOPS. Each of the colored columns represents a different IO stream, and the orange line shows you the changing queue depth over the course of the day. So when you look at the retail web portal workload, it is essentially a collection of much different events, such as 2 a.m. backup, boot storm, daily transactions, evening activities, and close. You'll note that there's a large spike at 2 a.m. backup of 64K read-writes, and the overall read-write mix for all of the IO streams that occur is 65% reads. There are many, many, many IO streams in a real-world workload. In this case, there were over 5,000 individual IO streams and over 4.5 million IOs. To create this workload, we select the 9 most frequently occurring IO streams over the course of this workload, and they're listed on the left. These 9 IO streams represent 71% of the total IOs and 3.2 million of the 4.5 million IOs that are recorded. It's important to note that in a real-world workload, the IO stream combinations and queue depths change over the course of the real-world workload. So it's a constantly changing combination of IO streams and queue depths, i.e., it can be 64K at 2 a.m., it could be half K, 4K, 32K at 8 a.m., it could be 16, 32, 56 and a half, 10 byte, and so on and so forth. So it's not a constantly fixed workload as you have in a synthetic corner case workload. Looking at the next workload, this is a GPS nav workload. And just comparing the two pictures, you can see that the IOs, the blue dots, are in a much tighter band, around 10,000 IOs. And there's 4 IO spikes of sequential half K writes. The IO streams are a collection of smaller IO streams, and the 9 most common IO streams out of the 1,000 streams are shown on the left. There are 3.5 million IOs, and the 9 IO streams are 78%, or 2.7 million of the 3.5 million. And looking at the third workload, we're looking now at a VDI storage cluster, which is a composite of 6 storage drives. Here, over the total workload, we see that it's 75% writes. And when we look at the 9 most frequently occurring IO streams of the 1,223 IO streams, we can see that it's a 75% write workload, and there are 167 million IOs as compared to 3.5 or 4.5 million in the previous cases. The 9 IO streams are 65%, or 108 million of those 167 million IOs. So these are 3 very different workloads, and they're going to be applied to look at how the storage and the fabric processes these very different workloads. We will summarize the main characteristics of these workloads in subsequent test result slides. Okay, test results. So we're going to look at a comparison of MTU frame size. We're going to compare the 3 transports, and we're going to compare storage. When we compare the MTU frame size, we're going to be looking at synthetic corner case workloads as well as real-world replay tests. When we compare transports, we're going to be looking at a replay test, which is the recreating the sequence of combination of changing IO streams, as well as a thread count queue depth sweep test, which takes the fixed 9 IO stream composite and applies it to every step of the test and varies the queue depth from 1 to 576. And then finally, we're going to be comparing the Optane to the NVM LUNs using the synthetic and the replay tests. So in our first comparison, we're looking at comparing standard and jumbo frames. So for the synthetic corner case, or random 4K read-write, and the sequential 128K read-write, we set the demand intensity at 128, or thread count 4, queue depth 32. In the first case on the left, we see blue and red columns. The blue column is standard 1500 byte, and the red is jumbo. So in the case here, you can see for random 4K read-writes, the jumbo is slightly faster than the standard. When you look at the sequential 128K read-write, the IOPS are substantially the same. By the way, if you want to turn sequential 128K read-write IOPS into bandwidth, you just divide the IOPS by 8, and that'll give you the megabytes per second. So 24,000 IOPS would be 3,000 megabytes per second. Note also that for the quality of service response times, the standard 1500 byte or blue column has very high response time spikes for the read workloads. So for random 4K read and sequential 128K read, you can see there's 147 and 429 millisecond response time spike. We'll discuss that more in detail later. When we look at the ROCEv2 comparison, we can see that the IOPS and response times, the standard and jumbo frames have substantially equivalent performance. And then when we look at TCP, we can see that for random 4K writes, standard frame is faster than jumbo. But for the rest of the cases, standard frame and jumbo are the same. And for response times, the response times are substantially equivalent. So essentially for MTU, 1500 byte standard and 1000 byte jumbo are essentially the same, except for the iWARP case where standard frames show very high response time spikes of 147 and 429 milliseconds. Looking at an MTU comparison, looking at the replay test of the 3 real-world workloads, again, remember, the replay test applies the sequence of IO streams and QDEPs as observed during the capture, and then we report a single average for the entire test. The workload characteristics, as you want to compare retail web to GPS to VDI cluster, are noted at the bottom. So the retail web portal is a 65% read, the GPS nav portal is 100% write, and the VDI storage cluster is a 75% write. You can see the block size content and the QDEP range listed as well. So in the first case, we're looking at iWARP. This is the Optane 1500 versus 9000 byte again. Blue is standard, red is jumbo. So for IOPS, standard and jumbo are substantially the same. There's a slight higher VDI standard than jumbo, but it's nominal. For response time, quality of service, again, standard and jumbo frames are substantially equivalent. When we look at the case for ROCEv2, for IOPS, for the GPS and VDI workload, which are the middle and right columns, standard is faster than jumbo. For the response time quality of service, they're substantially the same. And in the last case, looking at TCP, we can see that jumbo is faster than standard for the retail web portal workload, and the right-hand side, the VDI cluster workload. Again, the response times are substantially equivalent between jumbo and standard. So in conclusion, there is substantial equivalence between standard and jumbo, with certain cases where there's a slight difference, and in one case for iWARP, for 1500 byte, a peculiarity of a large response time spike for read workloads. Looking at offload versus onload, RDMA versus TCP, we're going to look at synthetic corner case and real-world replay test. So on the left-hand side, we can see the synthetic corner case. The two blue, or the blue and teal, are RDMA for iWARP and for ROCEv2. The orange is TCP. So for the synthetic corner case, we can see for random 4K write and random 4K read, RDMA is higher IOPS than TCP. When you look at sequential 128K read write, you can see that RDMA is similar to TCP. And in all cases, RDMA has faster response times than TCP. Looking at the 3 real-world workload replay tests, you can again see that the RDMA are faster in IOPS than the TCP. Both the iWARP and ROCEv2 are faster than TCP orange. For response times, you can see again that RDMA has faster response times than TCP. All of these results are expected results based on the onload, offload technology of the transport. Looking at demand intensity outside curves. So what are we talking about here? We are talking about a test that's called the thread count QDEP sweep and uses real-world workloads. So remember, we had 9 IO streams that we selected from the many thousands of IO streams, and they all occur at a different percentage. we fix those 9 IO streams in a composite. So if it was 25%, 10%, 5%, 3, 2, 1 of 64K, 8K, 16K, et cetera, every step of the test will have the same combination of IO streams at the associated percentage of occurrence. So we run those workload steps to steady state, and then we change the queue depth from 1 to 576. And as we increase the queue depth, we can see the IO rate or IOPS and the response times change until we saturate the storage with high queue depth, and we can see the IOPS stop increasing and the response times increasing at a very high rate. A picture is worth 1,000 words. So here's a retail web portal. Each line is a different transport, and you can see they all basically have the same curve. On the left-hand side is low IOPS. On the right-hand side is higher IOPS. At the bottom is low response time, and the top is high response time. So you can see that all 3 demand intensity curves increase in IOPS from left to right until they reach about 140,000. And then even though you keep applying more queue depth, the IOPS don't increase, but the response times start to dramatically increase. And in fact, for the green TCP, it has the highest IOPS at the lowest response time, but as we overdrive it with queue depth and saturate it, we can see the IOPS actually regress or go back below 140,000, and the maximum response time be higher than RDMA. So at the top, it goes above 4 milliseconds for the TCP. Looking at a GPS nav portal workload, you can see that all 3 transports have very similar DI outside curves, again with TCP having the best lower right-hand corner positioning. So lower right-hand corner means more IOPS and lower response time. Comparing to the retail web portal, you can see we're having almost 450,000 IOPS for the GPS nav workload versus only 140,000 for the retail web. So this is due primarily to the IO stream content. Remember, we said the GPS nav has smaller IO streams that are in the narrower range, and we have a wide variety for retail web, 64K all the way down to half K. And in the last case, we can see for the VDI cluster, they all have a similar DI curve. Again, the green TCP IP having the best lower right-hand corner case. However, the IOPS are less than 200,000. So from a broad view, you can see that for the middle case, we get 450,000 for a GPS nav workload. On the right-hand side, you get 180,000-ish IOPS for the VDI storage cluster. And then for the retail web on the left, you only get 140,000 IOPS. In all cases, the demand intensity outside curves are similar. Okay, let's look at NVMe storage LUNs and compare the Optane to the NVMe. Looking at the corner case test for the iWARP, you can see that Optane, the blue, is faster than the red for random 4K write and for 128K write, and nominally for 4K read, but they are the same for sequential 128K read. So again, blue is Optane, red is NVMe. Blue is faster than red for the first 3 cases, but equal on the right side for sequential 128K reads. Again, we note the high response time spikes for the 1500 byte MTU for iWARP. You can see the read workloads, 4K read and the 128K read at 147 and 429. This artifact is due to all of the factors in the stack, and it's beyond the scope of this study to isolate the cause of what that is. In the middle case, we're looking at ROCEv2. So here you can see blue is higher than red in the first 2 columns, and additionally in the third column, 24,000 to 17,000, but substantially equal for the right side. So again, sequential 128K reads are the same, but for the 4K read write and the sequential 128K read write, Optane is faster than NVMe. You can also see that NVMe has higher response times for the write workloads. And in the last case, we're looking at TCP. Here, blue is bigger than red in the first and third column. Red is bigger than blue in the second column. And again, they're the same for the fourth column. So in the fourth column, in all cases, sequential 128K reads, Optane and NVMe have the same IOPS and slightly faster response times for Optane. For TCP, you can see that it's faster for 4K reads. So TCP has the same for sequential 128K reads and slightly faster for 4K reads, being optimized for read workloads, whereas Optane has better performance at smaller bulk read-write performance across the board. Finally, we're going to look at the demand intensity outside curves for the different drives. And here you're going to see where the DI outside curve can really show you some clear differences. In the left side for the retail web portal, the dotted lines on the left represent the 3 transports for NVMe. The solid lines on the right are the DI curves for Optane. Clearly, you can see Optane is 140,000 versus 40,000 for the NVMe, and you can see the response times are much faster, all below 1 millisecond for Optane and 2 to 3 milliseconds for the NVMe. Note that the response time scale is log. In the second case, for the GPS nav portal, again, you see a wide separation showing higher IOPS, 450,000 for Optane versus only 50 to 60,000 IOPS for NVMe, and response times clustered between 0.1 and 0.5 milliseconds for Optane and well above 1 millisecond for the NVMe. And then finally, looking at the VDI storage cluster, all of the IOPS and all the transports converge around the 175,000 IOPS range, which means that both the Optane and NVMe are processing the VDI storage cluster workloads in equivalent number of IOPS, but the NVMe has a little bit slower response times than the Optane. So you can see that for a workload that has predominantly write with traditional storage IO block sizes, that the NVMe drive takes advantage of these read workloads and performs just as well as the Optane. But the Optane has a much wider range of performance, outperforming NVMe in the previous 2 workloads where we had 65% or 100% read and write, and a mixed workload block size that includes higher block size. So, in conclusion, what are our findings? For MTU, standard and jumbo are substantially equivalent. We saw that there's a case for iWARP random 4K reads showing large spikes, but across the board, jumbo and standard frame sizes are substantially equivalent. Second, looking at the CPU offload versus onload, we can see RDMA has faster response times and IOPS than TCP. In the third case, looking at demand intensity, we can see that demand intensity outside curves are similar for the 3 workloads, and that all workloads and all drives fully saturate by showing very high IO response times at the peak queue depth of 576. This is where the curves go up to the right, and they go up very high, so you can see that we've saturated the drives because the IOs do not increase anymore, but as the queue depth increases from the optimal IO point to the maximum of 576, the response times go very high. In the individual SSD spec, we saw that the optimal queue depth for Optane was 16, and for NVMe it was 256. But in the actual test, we saw Optane had optimal performance between 16 and 64 queue depth, which is much higher than 16. And the NVMe had optimal performance at the 80 to 96 queue depth, which is much lower than 256. So these differences in optimal outstanding IO are due to the nature of the workload, the changing combinations of IO streams, and the block sizes of those accesses. And then finally, looking at Optane versus NVMe storage, the LUN performance is much better than the SSD specs. That's because primarily you have a large IO pooling of IOs in RAM. Optane is generally superior to NVMe, with the one exception of the VDI workload where the NVMe and the Optane were substantially the same. For the synthetic corner case, Optane is faster than NVMe. For the replay test, NVMe and Optane were similar for the VDI workload, but in all cases, NVMe had slightly higher response times. So these are the findings we had based on that quick overview of NVMe over Fabric with host factors. If you have any questions, you can contact myself at info@calypsotesters.com or directly by email. So thank you very much, and be sure to fill out the questionnaire form to ask your rating of this talk. Okay, we'll talk to you next time, and have a good day.